All right, so let's take a look at part 2, 6.2, the Bohr model. So the Bohr model is based on 3 postulates. So Bohr basically said, all right, well, energy is quantized. So we need to look at the Bohr model is not really true anymore, but we're going to pretend it is for now. The Bohr model basically says, all right, I've got this nucleus and I have these orbitals of electrons around the outside, and we're going to see why it's not true. So you have a continuous set of orbitals. What he typically does is he's going to take a swath of this and just look at these energy levels right here. And that is the Bohr model. Essentially, well, this is n equals 1, this is 2, this is 3, this is 4, this is 5. So 1 would be like the lowest state of energy, and energy is increasing in that direction. So he's basically saying, all right, electrons are allowed to have an energy equal to 1, 2, 3, 4, 5. So they have specific energies. They're what we say as chemists is we say the in-between parts right here. This space right here in between all of these little in-between spaces are forbidden. So you should never find an electron in there is ultimately what the Bohr model states. Those are forbidden zones. They're only allowed to be in those discrete energy levels. Like when you're going on the elevator, unless it's the co-elevator, as it turns out, you can only get off on floor 1, 2, 3, 4. You can't get off at 2.5. Okay, so that same thing holds true for electrons. So Bohr basically said, all right, this is what an atom looks like. Let's take a look at the 3 postulates that he had. First of all, only orbitals of certain radii corresponding to specific energies are permitted, and that's what I just said. So electrons, following this equation, we can determine the energy of an orbital. So if it is n equals 1, if we're at the energy level 1, you can plug it in here and you can get the energy of that energy level. N equals 2, n equals 3, n equals 4, all the way up. Okay, an electron is permitted. In a permitted orbit is allowed, and the electron does not radiate energy, therefore does not spiral into the nucleus. So an electron is allowed in an allowed energy state, does not radiate energy, and therefore does not spiral into the nucleus. So if it's in one of these states, it's going to hang out there for a number of reasons. Okay, energy is emitted or absorbed by the electrons as long as the electron changes from one allowed state to another. Energy is emitted or absorbed as a photon. So we're going to see is energy is emitted, and that's the important part here. Energy is emitted or absorbed as a photon with this energy right here. Okay, so as long as we have from one allowed energy state to another, as long as we have a state jump from 1 to 2, 2 to 3, 3 to 6, whatever it happens to be, that's an allowed jump, then we're going to emit or absorb a photon. And we'll talk about emission or absorption of photon in just a second. Actually, let's just briefly talk about it. N equals 1, n equals 2. If I have an electron here, in order for it to make it to the higher energy level, it has to absorb a photon. So the electron, step 1, the electron absorbs photon. Step 2, electron increases in energy. And step 3, electron moves to higher state. That is the absorption of an electron, or of a photon, I should say. And so now the electron resides up here and all is happy. That's the absorption of a photon. If we look at the opposite case where the electron is currently up here, if it drops to a lower state, as soon as it drops, it emits a photon. Okay, so we're going to talk more about this, but that's how an emission occurs. It goes from a high state to a low state. In order to lose this energy, so whatever this energy happens to be, that delta E right there, that photon equals that delta E. So the energy lost comes out as a photon of the same energy. Okay, so ultimately what this means is absorption or emission of a photon. We can determine the energy of a photon by looking at this equation right here. Basically what we're doing is nothing fancy. We're looking at the energy of where it started, looking at the energy of where it ended, and ultimately that leads us to the overall energy change. So for this one, I have two examples down here. Calculate the energy occurs when it falls. What is the wavelength associated with the light above? What are the limitations of the Bohr model, which we're going to talk about briefly. But in a hydrogen spectrum, let's take a look at what we have. So first of all, we have energy on the left-hand side, or going from top to bottom, I should say. So this is going to be my n equals 1, n equals 2, n equals 3, 4, 5, and 6. So we have 6 energy levels. Okay. By the way, up here, these energy levels, I stopped at 6, but the next one would be even closer. The next one would be closer to that, closer and closer and closer and closer until we reach ultimately infinity. When you reach infinity, that means it's detached from the atom. It's no longer near the nucleus. Okay. But as you go up, they get closer and closer and closer together. You see this massive gap between 1 and 2, and then it gets much, much closer. Okay. So the energy associated, we could calculate the energies associated with these because we have the equation for it. So the energy of an atom is equal to negative 2.179 times 10 to the negative 18th, 1 over n squared. But of course, we know what that squared is. We know what that n squared is. We know that this is equal to 1, right? N is equal to 1. You calculate the energy for that. So you can calculate the energies for all of these. And we're probably going to do that. We're just going to do it in Excel. Okay. All right. Again, yeah, and then we'll take a look at an energy change in just a second. So if you have a photon dropping from 2 down to 1, okay, so n equals 2 down to n equals 1 versus an electron dropping from 3 to 1, 4 to 1, you're getting the idea here, 5 to 1, 6 to 1. That system right there is known as the Lyman series. And that's basically transitions to end at n equals 1. If we drop to n equals 2, if you drop down to n equals 2, oh, I don't know why it's not doing it. One more time. There we go. This is known as the Balmer series. BHLMER series. This one ends at n equals 2. And then the next one, dropping to n equals 3. I'm just going to do these quick. N equals 3. We call that the Paschen series. PASCHEN series. And there's a reason that this is important. So let's take a look at the specific. Let's take a look at this one right here. I think, is that the one that we do below? Sure, not really, but that's fine. Let's take a look at the Balmer series. The Balmer series transition. So delta E from 3 transitioning to 2. Okay, so 3 transitioning to 2 is equal to negative 2.179 times 10 to the negative 18th joules. And the transition, again, I'm just going to write the equation down, 1 over n final squared minus 1 over n initial squared. And just so I don't have to rewrite that, well, I guess I'll just rewrite it because that's what I do. 2.179 times 10 to the negative 18 joules. Going from the n final in this case, right? So n final is n equals 2, and initial is equal to n equals 3. See where I'm getting those numbers? So the n final is 2 squared minus 1 over 3 squared. And if you do the math, what you end up with is negative 3.02 times 10 to the negative 19th joules of energy. So that's the energy gap between there. Okay, so if it's dropping, if it's going from a higher state to a lower state, what that means is it is released energy, okay, because the sign is negative. So a delta E, if it is negative, that is a release of energy. And very specifically, it is a released photon. Okay. If the delta E is positive, because it went the other direction, it is an absorption of a photon. So the only way to make the jump from n equals 2 to n equals 3 is to absorb a photon that has the energy of negative 3.02 times 10 to the negative 19 joules. Okay. Take that one step further, and I'll try to remember to ask you, but what is the wavelength of something that has negative 3.02 times 10 to the negative 19th joules of energy? Okay. So let's take a look, try to solve these two problems here. And in fact, I already asked you to solve for wavelength, so just do it again for the transition from 5 to 3. In terms of limitations of the Bohr model. So de Broglie asked, Louis de Broglie, I just want to make sure I get his name right. De Broglie asked, okay, if light can be viewed as both wave and particle, have both wave and particle properties, why can't particles of matter, such as an electron, be treated the same way? So de Broglie basically said, all right, we have really fast moving particles. They should behave the same way light does. And in fact, what he noticed is fast moving particles need to be treated as waves to get a good basis of understanding. So the limitations of the Bohr model is it doesn't really treat the particle-like behavior. It just looks at light as a wave, and in fact, it does act as a particle. So that next step is going to be to take that wave-like behavior and turn it into, add momentum to it, because an electron does in fact have mass, therefore it has momentum, and look at an electron acting like a wave and how we kind of reconcile that with an atom.